Today we're going to talk about inverses. Inverses are functions that cancel each other out. You've probably talked about inverse operations before, like addition and subtraction, multiplication and division, even square and square root. All of those things are inverse operations. The reason we say that is because if I take a number like 4 and I square it, I get 16. Then if I take 16 and I square root it, I get 4. So square and square root are inverse operations because they cancel each other out, meaning the number I started with before I squared and then square rooted is the number I get at the end of the problem. Now, graphically, inverses mean you're going to switch your domain or x values and your range y values. So notice in this example I have here, in the first point, it is 2, 0. That point has been switched to 0, 2. The x and y values have just been switched. 3, 1 has become 1, 3. And 2, 4 and 4, 2 also match up. It's true to say that the first set is the inverse of the second set, and also the second set is the inverse of the first set. Inverses are a bidirectional relationship, so if two functions are inverses, you can work in either direction. Now, when we're looking at a graph of an inverse function, you can see from this example here, I've still switched things around because this point here was -2, 0. It's been switched on the other graph to the point 0, -2. Just for one other example, if I took another point over here, like the point 4, 2, that point has been switched on the other graph to the point 2, 4. So that's what it means by inverses. Both coordinates have been switched. What this means is it's going to reflect across the line y equals x. This line y equals x is the dotted line you see here on your graph. And that's like your perfect diagonal. It makes a 45-degree angle with your coordinate plane there. And if you fold it across that diagonal line, you could see that this piece here would line up with this piece here. And it's also true that this piece over here, down at the bottom, would line up with this piece here. So if you folded the graph, the two parts of the graph would fold on top of each other and be an inverse. Now, it is also true then that if two functions are inverses, they will have an intersection point on that dotted line, y equals x. If they do intersect at all, it will be one of their intersections at least will be on that line. Okay. A couple more things about finding an inverse graphically. Okay, so to find the inverse of a graph, it's helpful to write down a couple points. I'm going to do the two marked in purple on this first graph. You have the point 2, 0, and then the point 0, 3. That's my original function called f of x. And then the inverse, I use the notation f -1 of x. And f with a -1 just means the inverse of that function. So instead of having 2, 0, I'm going to switch them and have 0, 2. Instead of having 0, 3, I'm going to have 3, 0. Then I'm going to graph my 2 points. So 0, 2 would be there. 3, 0 would be there. And then I will do the best I can to get a straight line. Something like that. If you wanted to, you could graph the line y equals x. And what you should see is that the two functions intersect where that is. And if you were to fold the graph across there, they would fold on top of each other, where these two pieces here would fold and meet, and these two pieces here would fold and meet. So that's how you can do the inverse of a graph. The next one I'll let you try on your own. On the last one, I'm going to help you a little bit. Just pick a point. So this one is a 0, 1 is this point here. And then another point I can tell exactly is the point 1, 2. So I'm going to switch those points. So I'm going to have 1, 0 and 2, 1. I'll graph the point over 1 up 0. And then 2, 1 is there. And then what you're going to end up with is a curve that goes kind of like this, where it's a lot of times it's been flipped, but you can see it goes through y equals x and reflects.